Well, welcome here, back. The next presentation is from Mike Benjamin from Level 3 Communications about Border Gateway Protocol. Won't make it a long introduction because he will need the 30 minutes. Mike?
Thank you. Like we said, we're here to talk about BGP, which is how route exchange happens in the backbone of the internet. It's how we decide how traffic gets places. So a little bit about me. I'm a former network architect, so I spent a lot of time on large-scale networks, did a small amount of IETF work on BGP, so I have a lot of knowledge and background. I live here in the area, so welcome to Colorado. Sorry our weather is a little rainy and drizzly today. This is work I did in my spare time. This is not something that I'm speaking on behalf of my company for. So what is a BGP hijack? BGP hijacks are when someone announces a route in the internet that they do not own. So in our example here on the screen, AS100, the autonomous system, which is an identifier for an individual network, they own the 1/8 route. They're announcing that to the internet, and they're saying, hey, I know how to get to all of those IP addresses. AS600 comes along as a malicious AS and announces the same prefix that they do not own. And they say, hey, no, I know how to get there. And so in that example, where they're both announcing the exact same route, BGP path selection will occur, where each individual router and each individual network will make a decision on should I go to AS100 or should I go to AS600? And we'll end up in a state where the internet sends some traffic to the real destination and some to this potentially malicious destination. That's what we call an equal prefix length hijack. The second example is where the AS600 announces a more specific hijack. This is where the bit length, or the /24, is a longer match on the IP address than the /8. In this case, the router will install both prefixes. It will install the /8 from the real owner, and it will install the /24 from the malicious announcement. And when packets arrive at the router destined for anything in the 1.2.3.0 range, they will all go to the malicious host. There'll be no decision making. Everything will be hijacked. So here's an example of sort of a worst case scenario when we look at BGP hijacking, and I'll explain it. We have a laptop over here on the right that is a user trying to go to a server in the bottom right at the address 2.2.2.2. In a normal routing condition, the AS300 router would see the route announcement for the 2/8 coming from the bottom right and forward the packets happily to AS200. However, our malicious AS600 came along again, and it is going to announce a more specific route, which covers the 2.2.2.0/24 prefix. That prefix announcement is a more specific match, and now the AS300 packets will actually forward to AS600 to our malicious host at the top left. Now that malicious host has a problem. AS600 thinks that that traffic should go to the malicious server. So the server has two choices. Either that network needs to be set up in a way where some of the routers route it to its real destination, or the server needs to tunnel out of its network and send it back to its real destination. The reason this is a worst case scenario, obviously beyond just simple man in the middle where we can do payload injection, where we can sniff packets, et cetera, is that AS100 and AS200 have no idea this is happening. In this picture, AS600 has only announced the malicious hijacked route to AS300. So the only people that would have any visibility to this going on are those two networks. The rest of the internet would be oblivious, and the victim, in this case AS200, would have no visibility. So why does this stuff happen? Like with anything, the most often occurrence is people don't run their networks properly, people don't clean things up, people make typos, very simple scenarios. There's been some historical reasons where people redistribute things into other routing protocols and send them back into BGP. But ultimately, the most common occurrence is mistakes. The bottom example of a DDoS mitigation is the one situation where this happens for a relatively good reason, where DDoS mitigators would actually like to take their customers' traffic and clean it. And so somebody that's under attack, somebody will hijack that prefix, pipe it through a cleaning infrastructure, and then most likely tunnel it back to the real owner. This is a popular way that DDoS mitigators provide service. And then the mechanisms in which we can stop hijacking are relatively simple. Every router has a way to filter what routes should be sent. So networks can ask their customers, what do you own? And then filter them to just that IP space. Therefore, their customer can no longer hijack people on the internet. This works great when it's a small network at the end. When you talk on some infrastructure scale, we're talking thousands of prefixes that are changing constantly. The filtering methodologies become a little more difficult. And in some cases, we have networks in the world that aren't filtering anything. And this is where some of our problems occur. So I set out to write a hijack detector to be able to look at the backbone of the internet, because I wanted to define the question that we start off with: how vulnerable is the internet? How big is this mess that's being created? And so to write a hijack detector, I need to know who should announce a route. Who is the real owner? So I went out in search of, great, what's the record that I can look at? What's the ground truth of ownership? And realistically, it doesn't exist. And this is the root of our problem. So RPKI is technology we'll touch on a little bit more at the end of the deck, is a full cryptographic trust towards ownership. It's great, it works perfect. However, it has little adoption. 6.7% adoption is not where it needs to be. IRR is a little more of a legacy technology, similar construct. People register their autonomous system in a registry and say, these are the prefixes I own and should announce to the internet. Unfortunately, these registries, while there's a pretty good barrier to entry, to sign up and get your account for your AS, you have to prove ownership. Once you're in, some of them allow a pretty ad hoc assignment of route announcements. So whether your account to that system is compromised, you are malicious, or you typo, we still are in a situation where route hijacks can occur even in the face of the IRR system. Unfortunately, the biggest predictor of who owns IP space in the internet, and from an autonomous system perspective, is who announced it yesterday. And that's not where we need to be. Obviously, that's a horrible trust model. So if we need to predict ownership based on what you did in the past, I needed to create a baseline for my hijack detection. So I went through and I used the University of Oregon route views data. It's a great resource. They offer freely available massive sets of BGP data. RIPE over in Europe offers a very similar data set. And I grabbed one full routing table every day over the course of the time period and registered who owned it and who did they connect to. You'll see why I cared who they connect to in a moment. The next thing I did is, now that I know who should announce it based on history, is great, let's look at every BGP update and see if they match that data set. So the first check is, were you the person who announced it in the past? Great, then you're the owner. We're gonna go ahead and count you as acceptable. The next was, did you have one of those IRR records? You saw that about 2/3 of the internet or so is actually registered with an object in that system. So we could use that as a secondary filter on the data set. Then, this is where the uplink data came into play. I made the assumption that if a network was hijacked by its direct uplink, or most likely its own service provider, that business relationship was a reason for that hijack. Now, I knowingly introduced some false negatives into the data set by removing that. However, it's a small percentage compared to the amount of false positives that are left in the data set by not putting this check in. So both the uplink and the downlink make that very similar assumption. And anything that falls out the bottom without any of those relationships or records existing, I assume is still a real hijack. So I ran this over 5 years, from mid-September 2011 through just a few weeks ago here in 2016, and I was pleasantly surprised that less than 0.5% of the route updates in the internet actually exhibited a questionable behavior. And of that 0.5%, I was able to further refine it by 1/3 of those had the IRR object, 11 and 14 had those business relationships, and then 42% of the remaining set was an unknown, where I believe that was a real hijack as far as the system was concerned. Now, I had a benefit of being able to see the future. So you'll notice I stopped on September 15th. So I was able to baseline all the way through September 30th. So baselining through to September 30th put me in a position where I could see who owned it 15 days into the future. And so I was able to further reduce it by another 50%. So the end state is I had a data set that was 0.09% of all route updates for 5 years were believed hijacks in the system. This is interesting because if you were to implement a real-time route hijacker, I know you'd have a 50% false positive rate based on this data set. That's not a good place for us to be, and this is sort of why I'm here talking about the problem, is we need to be working on improving the state of this internet routing. Over on the right, we do have some good news, though. If people want to actually look at this data set, a couple hundred records a day is a consumable data set. When that's broken down to the per company, per entity group, that's something a human being can actually analyze. A couple prefixes a day, a couple routes a week, or at larger companies, we're still talking tens, not millions, not thousands. So that's very consumable. It's important to point out, as I do the year-over-year comparison, the internet routing table grew about 85% or so over that time period. So even though it's doubling, it's not in a completely different class of growth than normal route table growth. So now I wanted to look at the data. What was the largest day of route hijacking in that 5-year time period? So I sorted by the amount of prefixes on a single day from a single autonomous system that was believed to be a hijack. And as you can see, we have some big ones, and we very quickly drop off down to some relatively small ones. And I was very happy to hear when I looked at the data set that I could find some news articles about these. My hijacker actually worked. However, I wanted to know why 6 of them did not have news articles. So I added this right-hand column, which is the number of ASES paths. This is important back to our example of the man in the middle, where we talk about scoping of route announcements. If the entire internet does not see the rogue announcements, it's unlikely that many people are going to notice. It's unlikely to get a news story published. So as we look at some of these with single-digit amount of autonomous system paths seeing the hijacks, that explains why there wasn't a lot of visibility to them. Then I wanted to know who are the worst autonomous systems, a single AS over the entire 5-year period who hijacks a lot. I thought maybe I'll find a malicious autonomous system in the internet. And I'll tell you, as somebody who does a lot of data analysis, somebody who spends a lot of time looking at stuff, when you see one entity rise to the top, you get really excited. You think you found what you're looking for. And the United States Department of Defense, by far, I believe they were 16 of the top 17 ASs. Unfortunately, when I dove into adding that middle column, they're hijacking themselves. So all of the autonomous systems that are in there, and this goes back to hygiene, they are doing something in their route announcements where they are either moving things around without updating IR records or RPKI, or they're in a position where they have multiple autonomous systems on one network, which you're not supposed to do. The MTN, a service provider out of South Africa, was in the exact same situation where MTN had 2 ASs and they were hijacking themselves. So not as exciting as I'd hoped I'd found. I did go through and, I'm not sure how well you guys can see that, but I did go through and pull some IP addresses. Now, caveats here are this is a single point in time resolution of these domains from one EC2 host off AWS. This is not using passive DNS throughout the entirety of history. So relatively poor example of hijacking the entirety of Google or Twitter. But as you can see, this is not a huge list. So for those single IP addresses, we have some relatively small amount of hijacks that have occurred over 5 years. The last one is particularly interesting. While I was doing the work, Brian Krebs posted an article that was about a booter service. If you're not familiar with what that is a place where you can buy access to denial of service people. Nice little web page where you can click a button and knock people off the internet. And this company was called VDOS. And they one day decided to DDoS a company called BackConnect. And BackConnect, their weapon of choice to attack back at VDOS was a BGP hijack. So BackConnect decided that they would hijack VDOS's IP space in order to stop the attacks against their infrastructure. It's the first time I am aware of that it was used as a weapon with someone very openly saying, yes, I did it. And so this even further brings to the forefront why we need some technology in order to improve upon this situation. Good news, of course, I had to show you some sites that had no hijacks in the history. So some popular sites for some of the people in the room. Virus Bulletin, of course, being nice to see at the bottom. That IP address showed no history of hijacking either. But the bad news is, everything I just showed you doesn't matter. You can manipulate the ASES path. The ASES path attribute is something carried with all BGP route announcements, and it records the path of every autonomous system a route has gone across. And that's what I used to define the origin AS for my hijack detector. That's what I used for defining the uplink AS. It is very easy to manipulate, and there is nothing in the RFC for BGP that states you can't change it. There's no validator around cryptography or anything else that allows this to not be manipulated. I was really interested to see how quickly I could change ASES paths, and so I downloaded Quagga, which is an open source routing software. It's what that University of Oregon route views system actually uses behind the work it's doing. And in about sub 5 minutes, I was able to piece through where the struct was and what function and where I could manipulate ASES path. That's how easy it is to modify ASES path. Now, of course, Our large-scale routers in the backbone of the internet are not open source. It's not as easy to get into them. But the folks who may be going after this from a malicious perspective sit at the edge. They're not in the core of the backbone. So I've updated the picture here at the top right as an example. And our guy here, our bad AS600, you can see the AS path that it places on the route announcement to AS300 is 600, 200. So the right hand is the origin. So it's saying that this route came from AS200. However, I've also introduced the network topology to show that AS600 doesn't interconnect to AS200. It's made up what that route announcement is. So all of the hijack detection that we can do based on AS path, we can't trust. So anyone with this level of sophistication to actually modify the software of their route announcements can manipulate this AS path. So now that I've depressed you, I always enjoy when a security talk actually talks about how to fix it. So this is how we fix it. The first thing we have to do is have a proper store of who owns stuff. So cryptography is a great model for defining who owns things. This is based on existing PKI standards. If you read through the RFCs, as I painstakingly did for this talk, you'll see a lot of references to existing methodologies and existing standards around cryptography, which is really good to see. People aren't going to invent their own trust models. So ultimately, what happens here is the RIRs, which I have not spoken about yet, are entities that are allowed to own IP space. So IANA sits as a part of ICANN and owns all IP space in IPv4 or IPv6. It suballocates chunks of it to a variety of groups. You'll heard of them called ARIN, RIPE, AFRINIC, LACNIC, and APNIC. They are the local registrars for IP space. They provide the root trust for this cryptography model. And at the root of that, they then suballocate IP space to networks, which networks can then suballocate, and you'll see the nice trust chain in your certificate signing. The final end of that trust is something called an ROA, or a route origin authorization. You can think of this as a relatively simple document that contains two pieces of information. It contains what the route is, along with how long it can be, and then the AS that should announce it. So back to our example, AS100 would say, I can announce 1/8, and in fact, my network guys at some point may want to break that into some pieces, so I'll allow /8 to be all the way down to /12. So they'd create an ROA that says 1/8 through 1/12 is allowed to come from me, and I'm AS100. They would sign that, and now we can validate who the real owner of it is with complete trust. Obviously, we got some work to do on this standard as it's only at 6.7%, but it is available for most router software and most environments today. Next, we need to validate that path. If anybody can make up whatever they want about the path, we need to be able to do the same methodologies around trust for the path itself. This, unfortunately, is not out of IETF yet. It is not in RFC. It is not implemented. So what this does is it signs AS by AS. So each network, as it needs to update the path, because the prefix is transited a network, it says, I'm going to sign the route, and we can go back and look at that trust at the endpoint, and we can use this for route validation. So we can throw away routes that are not signed. There's a few problems with BGPsec. The first is, if I'm going to validate the path, every network in the path has to be running this. So if anyone has tried to get the entirety of the internet to implement something before, this is not going to happen overnight. We've got a lot of work to do to get networks around the world to actually implement this. The plus side is you can validate paths in intermediate hops if subsections of the networks do implement it. The other downside is cryptography is not cheap when it comes to processing. So we've got routers that in many cases have very underpowered processors, very small amounts of RAM, and what we just ask them to do is carry a lot of extra information and do a lot of signing as they have to sign each prefix as it goes out to each path. That's a lot of work for some of the legacy technology out there, and in some cases, networks will have to remove and replace routers in order to get this to function, furthering that burden to our internet-wide rollout. So there's one other area which I thought was worth talking about, which is what IP space should actually be there in the first place. So there's a class of IP space that just should not be routed in the internet. You should not see a packet from it. You should not source data from it. And so we call these bogons. You're all familiar with the most famous set of bogons, the RFC 1918 space, your 10/8s, et cetera. However, there's a lot of space that's unallocated by those RIRs, the regional registries. They've got some /24s they have not handed out. They've got some that are reserved for special purposes, and you should not see anything from that. So I ran the same, I don't think I said the number earlier, but it was about 40 billion BGP update records through a radix tree that looked like the allocated IP space and spit out the other end what IP space should not be in the backbone of the internet. You yourself can download these at these FTP servers. They are available on an everyday basis. I think there was maybe about 8 holes in the data set over the 5-year period. But ultimately, they're available on a day-by-day basis, so I was able to accurately represent what IP space should be on every single day against the current BGP updates. Very similar size of problem, 0.08% of those BGP updates should not have existed. They just shouldn't exist in the internet. So of course I wanted to see who's doing it most. So the most announced prefix that should not be there is at the top. Looks somewhat similar to RFC 1918 space, but it is not. Each of these are things that just should not exist. In the case of that top one, it is not allocated. It doesn't exist in its entirety, and the regional registrar says it should not exist in the internet. A few of the others are interesting as you look through the list. Some of them, the owner, for instance, some of the Department of Defense routes, they own most of the routes, but there's a hole in the middle of their prefix announcement that they don't own, that is reserved. And whether it was legacy or laziness or a mistake, I don't know, but they are announcing even the section of the space that they don't own as a part of the aggregate route. So again, back to cleanup and looking at the internet, we got some work to do. So what do you do with this information? The number one thing I think is pretty widely something we could do in lots of things. Endpoint software, firewalls, routers. Block the bogons. That IP space should not exist in the internet. We should not be getting packets from it. We should not be sending packets from it. We should not have entries in our routing tables if we have anything other than the default routes. We shouldn't see this IP space in the internet. And if we all collectively spend the time to make it not exist and not be viable, those route announcements will go away. People will go clean their stuff up. Unfortunately, most of us are not blocking it. Bogon space is very popular amongst spammers. What a beautiful way to spam if you're a spammer. Then grab a prefix that no one owns, spam from it, and walk away. What are you going to do to that space? You're going to block it tomorrow? That's not something that's viable as a defense mechanism. So for the spammers, it's great. So people are actively using this for malice. And so it's yet another reason, not just, hey, let's make the internet clean, but this will actually help protect from known malice by not allowing bogon space in any of our equipment and any of our implementations. The next is, if you own IP space, watch it. I mean, I'm not an amazing software developer, and I was able to write a system that watched the entire internet. We're all capable of throwing together some scripts that watch our own IP space. And if you don't own IP space, watch your cable modem provider, your DSL provider. Watch some popular websites that you go to. Take a look at what's happening to the things that you access and use on a daily basis. Do they move around? Do people mess with them? I think you'll find some interesting things happen amongst any IP space that you spend the time to watch. Next is RPKI. Now this is specific to a network operator, but if you're not a network operator, asking your network operator when they're going to do this is important. Is to be able to say, yes, I own this and I'm the one that should be announcing it is an important thing that we get through, get that 6.7% up to a number where people can actually enforce it as a mechanism. If you are going to connect in the internet, you must do this. And so we need to get those numbers up before we can hit to a point where we do that, and everyone working on it will be a benefit to that. Next is BGPsec needs to continue its work in the IETF, become an RFC, and we need to implement it. It's going to be a long journey before we can fully validate the paths of all of our internet routes, and we need to start that journey at some point, not look at it with pessimism, and any help and any push that anyone can give is a positive thing towards that. And then, of course, encrypt your traffic. You knew this already, that's not an exciting bullet, but I'll tell you what, I talk to a lot of security people. I've got a lot of friends that work at a lot of different companies, and the knowledge of encrypt your traffic because somebody could look at it is common. I imagine everyone in the room knows that. But being able to articulate more clearly why is something that I hope you learn throughout this presentation. Now I said that anyone could go write some scripts to watch their IP space. These are the tools I use. I'm a Python guy, but there's a lot of things out there to be able to look at these files, to be able to process them, to build trees out of them and watch what's going on. Nothing revolutionary in this set of code, but I thought it'd be helpful to you all to listen. So with that, we actually do have time for questions. So.
We certainly do. Thank you, Mike, for your presentation. It was pretty clear.